Alright, so in this video I'm gonna be explaining another important article with the title Agent-Based Graph Neural Networks. This ICLR paper in 2023. We present a novel graph neural network we call AgentNet, which is designed specifically for graph-level tasks. AgentNet is inspired by sublinear algorithms featuring a computational complexity that is independent of the graph size. The architecture of the AgentNet differs fundamentally from the architectures of traditional graph neural networks. In AgentNet, some trained neural agents intelligently walk the graph and then collectively decide on the output. We provide an extensive theoretical analysis of AgentNet. We show that the agents can learn to systematically explore the neighborhood and that AgentNet can distinguish some structures that are even indistinguishable by 2WL. Moreover, AgentNet is able to separate any two graphs which are sufficiently different in terms of subgraphs. We confirm these theoretical results with synthetic experiments on hard-to-distinguish graphs and real-world graph classification tasks. In both cases, we compare favorably not only to standard GNNs, but also to computationally more expensive GNN extensions. So you see AgentNet architecture. We have many neural agents walking the graph. Each agent at every step records information on the node, investigates its neighborhood, and makes a probabilistic transition to another neighbor. If the agent has walked a cycle or a click, it can notice. For example, this is interesting. It says, I've been there 3 steps ago. And then I keep seeing these nodes. So each agent at every step records information on the node. For example, it says the green agent says, I see a triangle if it moves like this. And then, for example, the red one says, I didn't see a triangle, this one. Same as the orange one. I didn't see a triangle. But the problem of this paradigm is that you have many features, many complex structures like complex clicks, very complex substructures. How do you deal with that? So let's see what the paper says. The core idea of our approach is that a graph-level prediction can be made by intelligently walking on the graph many times in parallel to be able to learn such intelligent graph walking strategies through gradient descent. We propose the AgentNet model. On a high level, each agent is assumed to be uniquely identifiable and is initially placed uniformly at random in the graph. Upon an agent visiting a node V at time step t, the model performs 4 steps: node update, neighborhood aggregation, agent update, and agent transition. So first, the embedding of each node V sub I that has agent A sub I and it is updated with information from all those agents using the node update information F. So to ensure that the update is expressive enough, Agent embeddings are processed before aggregation using a function phi. So this one is agent embedding. Embedding of agent A sub j at time t minus 1. And then we aggregate here, then we update here. So next in the neighborhood aggregation step, current neighborhood information is incorporated into the node state using the embeddings of neighboring nodes. Similarly, we apply phi that on the neighbor embeddings beforehand to ensure the update is expressive. These two steps are separated so that during neighborhood aggregation, a node would receive information about the current state of the neighborhood and not its state in the previous step. The resulting node embeddings is then used to update agent embeddings so that the agents know the current state of the neighborhood, how many neighbors of V sub I have been visited, and which other agents are on the same node. So with V of A sub I being mapped from agent A sub I to its current node, now the agent has collected all possible information at the current node. It is ready to make a transition to another node. For simplicity, we denote the potential next positions of agent A sub I by n of AI. So first, probability logits are estimated for each V sub j. Then this distribution is sampled to select the next agent position. And we always use Gumbel softmax because of the sampling, any kind of discrete thing, because discrete things are not differentiable, so we use this Gumbel softmax trick. So we use this straight through Gumbel softmax estimator. In practical implementation, we use dot product attention to determine the logits. And to make the final graph level prediction, pooling is applied.